Okay, so we're going to be finishing up 6-4 in this conversation. And so I wanted to start with what we were doing on Friday, where you were creating a Ferris wheel. This is what I did, pretty boring. Radius of 20 meters, center of the Ferris wheel is 30 meters off the ground, 1 revolution counterclockwise in 30 seconds. So I didn't switch directions, I didn't do anything crazy, I switched from feet to meters. So this is a much bigger Ferris wheel, but other than that, it's pretty boring. Here's my graph. I went ahead and let the computer do it for me. And so you can see my midline at 30, which is the center of the Ferris wheel. And then it moves up to 50, which is 20 meters above, and down to 10, which is 20 meters below. These are actually not degrees because it's time, but the computer counts funny. And so when I switch to degree mode, it puts degrees on it. So you can see I'm reaching my bottom peak back to the middle in 30 seconds right here between 28 and 32. So this, let me mark some points. This is 30. This is 15. This must be 7.5. And this bottom peak is at 18. Wait, excuse me, I can add 22.5. And so that's kind of the idea, and you'd have your marks. And so you should, and how did I figure these numbers out? So 30 is my time it takes to complete a rotation, 15 is half of that, and half of that is my next peak at 7.5. So when you're looking at your graph to try to see if you're right, what you want to do is figure out the time it took for your Ferris wheel to go and mark that, and then go backwards in half. So if you had decided to go clockwise, your Ferris wheel would go down first, then up and back. So that's what a clockwise wheel does. It just goes down first. Because instead of getting higher, if you're going clockwise, you're getting lower first. And so that is the difference there. And so my equation, based on my information, I'm going to go ahead and use h of t, height, at a specific time. Now, I think we used h of t for our other equations, so if you want to use a different letter, because we want it to be a different equation, whatever works for you. I've got 30, my midline, plus my radius of 20, sine of something t. And to figure this out, I'm going to take 360 degrees, divide it by my period of 30 seconds, and end up with 12. So I've got 12 degrees per second. And so technically, I guess these are degrees, but that's the idea, 12 degrees per second, except for that these are actually seconds, so it's not counting by degrees. So just kind of keep that in mind with my graph, that these should not have those marks on. And that's it. So that's what you should have gotten finished on Friday. If you take a minute, compare your work, see what you did, see if your graph is right, see if your equation is reasonable based on your numbers. So whatever your center of your wheel, that's the center of the wheel. This is the radius of the wheel. And this is the time divided into 360 degrees. So those are where our numbers come from. Make sure yours is reasonable. It'll be different. Everybody go ahead, pause the video, check. We're going to move on and start talking about what these things mean. So we've been considering our task. We've got our basic situation. What happens to the graph when the radius of the wheel is larger or smaller? So my wheel has a smaller radius. And what that does is it changes the distance from the midline to the peaks. So it's changing the distance from the midline to the peaks. So we want to say something about that and what's happening. What happens to the center of the wheel? Where does that go? And what happens? And what happens when the wheel rotates faster or slower? So it'd be nice to have some comparisons. Maybe take everybody in your groups, run over to Desmos, make sure you switch to degree mode and plot them. So like you jump to Desmos and plot them. So this is the one we did together as a class. You know, I'm already in degree mode over here. I've set it so it counts reasonably, gives me my axis, and I've drawn my midline and my height. So like with my new graph, which you can't see me type it in, but bear with me. I'm going to change to g of x equals, and it was 30 still, plus 20. So I actually did not change my midline, sine of 12t. So 12x, excuse me. So by having them both, now I can compare them and talk about what changed. So my middle didn't change. I left it at 30. I'm in meters and this is feet, but we're going to ignore that part for just a minute. So the midline hasn't changed, but you can see that the distance from my peak to my midline is less than it was before. So that's what we want to be talking about right now, is going back. We want to make some sort of comment about what happened with the radius of the wheel. So that my radius is smaller, so what changed? Check out a larger one, see what changes. And then what would happen if I had changed the height? Now looking again at the radius, the speed, so mine is going slower. It's going 30 seconds, whereas the original was doing it in 20 seconds. And so what's the difference? One, it's taking longer to complete a cycle. It completes it there. The blue one has completed it there. And that's a big difference in those two completion times. And so I'm going to go ahead and turn off the two peak lines. But that's that difference. So it takes up, so since my radius, my time is taking longer, it's taking it longer to make that cycle. And this one's doing it more quickly. So those are our two known things. So it's just important to notice those kinds of things, what's happening. We can also see that everything's more spread apart. Mine's harder to graph because all the numbers were funky, but that's the kind of thing you want to be writing about right now, is what is changing. So take a minute, grab everybody's equations, run over Desmos, type them in, and see what's happening as these things change. We're going to ignore the fact that you might be in a different unit, measurements, and just kind of see what's going on. So just take a minute, plug them in, see what's happening. Make some comparisons and write down what you see. Go ahead and pause the video. Okay, so the radius, when the radius is larger or smaller, it's how far away we move from the midline. So those are the words we kind of want to be thinking about here, is how far away we're moving from the midline. I don't know why those were there to go away. Anyway, back we go. And then changes the height of the center wheel changes the midline. So we know the midline is that, so the height of the center wheel is the vertical shift. That's what I was going for here. I got distracted. So vertical shift. The movement from the midline, that is technically called the amplitude. And the time to complete a cycle is called the period. So those are the technical names: amplitude, vertical shift, and I spelled vertical shift, and period. Period's important. Period is probably one of the harder of these two. The midline's the easiest by far. Midline, vertical shift, that's the easiest. The amplitude is second, and the period is the hardest of these three that we're kind of studying right now. So moving on. Next it says, how does the rider's, so that's our change in the graph. The rider's height changes are very similar. So kind of think about that because since it's a graph of the rider's height. So the rider's height is more of a question of what's happening on the wheel. So think about on the wheel what's happening rather than what's happening in the picture as we plot the wheel, the movement, the person's height over time. But it's similar thoughts, so just kind of think about that. Write down what you think. I don't think there's right and wrong answers here because it's very similar. And then we want to try some. So these are other people's equations, and what you want to do is take a minute, read them carefully. This is what the quiz questions match, is to write the equations of the height on the rider in each of these situations. The radius is 30 feet, the center of the wheel is 45 feet above the ground, and the angular speed of the wheel is 15 degrees per second clockwise. So they've actually told you how many degrees it's passing through instead of how long it takes to complete a revolution. So they've already done the division for you in question A. They've told you the angular speed, how many degrees per second, which is what we find out when we take 360 and divide it by the time it takes to complete a cycle. So they've already taken 360, we're talking about this part, taken 360 and divided it by some time and gotten 15 degrees per second. And so we don't know how long it takes to complete a revolution, but the number we need is 15. So go ahead and try thinking about what I was talking about earlier when I was explaining where my equation came from. So these things, center, radius, time, that's degrees per second or angular speed. I probably should have said that. Okay, so go ahead and use that to answer part 5, to answer questions A and B in part 8. Go and pause, you can back up a little bit, whatever, and answer the 2 questions. Okay, so for A, I went ahead and called my equation A of t. I've got 45 plus 30 sine of 15 degrees t, because it already told me what my angular speed was, so I didn't need to calculate it. Didn't say rotations. And so I got 15 seconds, 45 being the distance above the ground goes there. The radius of the wheel went here, and then angular speed went here. The radius of the wheel is 50 feet, which goes right there. The center of the wheel is at ground level, so there's a 0. You didn't need to write 0. And then it takes 1 revolution clockwise, and I actually have this slightly wrong. I wanted to do that wrong on purpose. So clockwise every 15 seconds. So this is what we've done before. Take 360 divided by 15, you get 24, but it's going clockwise. So officially it's going backwards. Now you can think of it this way is correct, and this way is also correct. And this is because sine is an odd function. So if you recall about odd functions, when you plug in a negative value, you get out the opposite of what you would when you plugged in the positive value. So both of these would be considered correct, either changing the negative out here or putting a negative inside the argument. I find it, for my brain, it makes more sense to put it on the inside because I'm going the opposite direction. So I'm going to divide by negative 15, if you will, or maybe I'm doing a negative 360 degrees around the circle, whichever way makes you more comfortable to think of it as being negative. But that is my way of figuring out what's going on. So I hope everything's going well. We'll see you soon.